So in this lesson, we're going to continue looking at circuits, and specifically circuits that are made up of a voltage source or battery and various configurations of resistors. So our objectives for today, we're going to learn how to draw a schematic diagram, calculate power dissipated in a resistor, and then be able to differentiate two configurations or types of resistor circuits. One is called parallel and one is called a series. And how do we analyze those different types of circuits? And then the last, we'll be able to actually solve what we call series and parallel circuits for voltage, current, and or resistance. So let's talk about a schematic. A circuit schematic is a drawing of an electrical circuit using standard symbols for the circuit elements. So here's a very simple circuit pictured, right? We've got a dry cell battery connected with a couple wires to a light bulb. Now, the way we've drawn it is really a pictorial or physical representation of the circuit. We drew the actual battery, we drew the actual light bulb. Now, in a schematic circuit, we're going to use symbols for the actual items. So here's a symbol of a battery. It's normally some parallel lines alternating between long and short. And then we put a plus and a minus on there to indicate the orientation of the battery, right? Which end is the high electric potential. The symbol for a light bulb is a circle with a little loop inside. That little loop represents the filament, right? If you look at a light bulb carefully inside, now this is a old traditional incandescent light bulb, right? We don't use many these days. We're using LED light bulbs, but the traditional light bulb would have a small wound or coil of wire in there, usually tungsten. And when that heats up, it generates photons, electric energy is converted to light energy. So that little loop in there is meant to represent the little wire that is inside the light bulb. And then we just use straight lines to represent conductors that connect the elements of a circuit together. Okay, so here's our circuit schematic that represents a simple circuit of a battery connected to a light bulb or lamp. Now, you're not expected to memorize this, and we're not going to really use many of these, but I just want to show you that there is a whole library, right, of different symbols that we use for different electrical circuit components, right? We talked about voltage sources and connectors, meters, motors, and switches. So meters if we're measuring voltage, or the current in it, right, an ammeter, or a resistance meter that we measure ohms in, or sometimes called an ohm meter. And then we've got different elements like resistors, capacitors, and inductors. And then diodes and transistors are what we call semiconductors, right? So computer chips are made up of often millions of transistors or diodes that are all integrated onto a single piece of silicon. So these are the symbols for the transistors, LED diodes, or even a full integrated circuit. Now, the ones that we're going to use are primarily the battery or voltage source, the resistor, and maybe sometimes a light bulb or a switch that we'll put into the circuit, and a voltmeter or ammeter, depending on what we're trying to measure. So let's go through an example of a little more complex circuit and see what the schematic would look like, right? So if we just begin to walk around this, we start with our battery. It goes through a switch, and it goes through a ammeter. It's right, going to measure the current flowing through the wire, into our motor, through a resistor. That kind of funny sausage looking device is a resistor, and then back into the battery. And we also have a voltmeter measuring the voltage drop across our motor. Now, how could we redraw this as a schematic? Well, let's start with our battery voltage and then just kind of work our way clockwise around the circuit. So we've got a connector wire and then a switch. Okay, so this is a toggle switch, right? If we swing it down, it will close the circuit and allow charge to flow through it. We'll put an ammeter here that's going to measure current. Remember, if we're measuring current, the ammeter has to be in the same loop that the current is flowing. So we actually make it a part of the circuit. Through the motor, we use a circle with an M in it as a symbol for a motor. Through our resistor, right? The resistor is this kind of zigzag or sawtooth line, and then back to our battery. So we've completed the drawing of the circuit, the loop in which the current is going to flow, but then we also are going to attach our voltmeter, right, around both sides of the motor so we can measure what the voltage loss or the change in electric voltage potential is as the current flows through the motor and the motor uses the energy, right, that's in that charge before it goes back and gets re-energized by our battery. So there's an example of a schematic that we drew from a pictorial representation of the circuit. Now, let's talk a little more about resistors, right? In the previous lesson, we learned about Ohm's law and that we're able to find the relationship between voltage, current, and resistance. And the power in a circuit element is simply the voltage being provided by the battery times the current that's flowing through the battery, right? So P equals I times V. Now, if we wanted to find the power that is being consumed or used up by the resistor, remember the battery provides power and then the rest of the circuit is going to use that power. We can use Ohm's law, right? We have this little triangle to help us figure it out. So from Ohm's law, we know that the current in a circuit is equal to the electric potential divided by the total resistance, V over R. So if we were to take the V over R, right, and substitute that in for I in our power equation, we get this expression, P equals V over R times another V, or we could write it this way. The power through a resistor is equal to the voltage across the resistor squared divided by its resistance. Okay, so that's one way we could calculate the power in a resistor if we know the voltage across the resistor. Now, the other way we could do it is to substitute in current times resistance for voltage. So we would wind up with this expression. Power is equal to the current squared times the resistance. So if we know the current, we can use this formula to calculate the power in a resistor. So two forms, power dissipated in the resistor. We know the voltage across the resistor, V squared over R. If we know the current flowing through the resistor, I squared times R. So let's look at an example where we can apply this. A heater has a resistance of 10 ohms. It operates on 120 volts. So I want you to sketch the circuit schematic. And what is the power dissipated by the heater? Right? The heater is a resistance heater at 10 ohms. And what's the thermal energy that is supplied by the heater in 10 seconds? All right, so here's our schematic, right? We draw our voltage source of 120 volts connected across a 10 ohm resistor that represents the resistance of the heater. Now, to measure the current, right, we've got to put an ammeter in the circuit itself. And to measure the voltage drop across the 10 ohm resistor, we're going to connect our voltmeter to each side of the resistance. Now, the voltmeter has basically infinite resistance. So when the current is traveling through the circuit, it's almost going to be like it doesn't even recognize the voltmeter as a possible path for the current to travel through. Okay, so it has very, very, very high resistance. The current is going to say, oh, it's much easier for me to flow through the 10 ohm resistor than the voltmeter, which has nearly infinite resistance. Okay, so when we attach a voltmeter in this way, it doesn't really change the behavior of the circuit and how the current flows. All right, let's find the power dissipated by the heater. So since we know the voltage, right, the voltage drop across the resistor is the same as the voltage rise in the battery. So we know the voltage, 120 volts, and we know the resistance, 10 ohms. So let's plug that into our formula. And we're going to get a fairly large number here, right? 1.44 times 10 to the third watts, or 1.44 kilowatts. And it makes sense, right? The whole purpose of a resistor is to, a resistance heater is to generate heat. And that's what happens. We lose 1.44 kilowatts at any instant in time through the resistor. Now, to find the thermal energy, right, we know that energy equals power times time. So we're just going to take our 1.44 kilowatts and multiply it by 10 seconds. And we get 14.4 times 10 to the third joules, or 14.4 kilojoules. All right, now there's two different ways we can connect multiple resistors in a circuit. The first is what we call resistors in series. So if you think of series, think of the current has to flow through both of the resistors, but it's going to do it serially, meaning has to go through one first before it can go through the other. So to do that, the resistors have to be connected end to end. And notice we put 3 ammeters in our circuit, 3 different places we want to measure the current flowing through this circuit. And the question is, how would we find that current if we know the values for the R1 and R2? So let's start with Ohm's law, right? Current is equal to the voltage divided by the resistance. But in this case, the total resistance that the battery sees is the sum of the 2 resistors, R1 plus R2. So when we have a resistors in series connected end to end, to find the total equivalent resistance, we simply add the 2 resistors values together. So that's our first kind of formula here for working with resistors. Equivalent resistance for resistors in series is simply equal to the sum of the individual resistors, R1 plus R2. This works whether you have 2 resistors in series or 100 resistors in series. So let's look at a real example here. Can we calculate the equivalent resistance? Well, they're in series, right? The current has to flow through R1 before it can flow through R2. So to find the equivalent resistance, we're simply going to add the 2 resistors up. So 20 plus 20 gives us 40 ohms. So in effect, we could replace R1 and R2 with an equivalent resistance of 40 ohms. So let's look at another example. We have 2 resistors, 47 and 40 and 82 ohms, and they're connected in series across a 45-volt battery. So here's our schematic that shows that. 2 resistors in series, right, connected end to end. And we want to find what is the current in the circuit. So if we put our ammeter here to measure it, right, what is it going to read? What is the voltage drop across each resistor? Right? We know the voltage rise on the battery, 45 volts, but we want to know how much of that electric potential will be lost or dropped when we go through R1, and how much will be lost or dropped when we go through R2. What we also know is that the total voltage drop across both R1 and R2 has to be equal to the voltage rise in the battery, or 45 volts. So we, in effect, want to put voltmeters there and measure what those voltages will be. So let's look at the first one. We know the current in the circuit is equal to the voltage divided by the resistance, in this case, the total resistance. And since there's in series, we're simply going to add R1 and R2 together. So let's do that. 45 volts divided by 47 plus 82 ohms. And that works out to be about 0.35 amperes. So we know we have that amount of current flowing out of the battery through R1, through R2, and back into the battery. Okay, they all see the same amount of current flowing through the elements, whether it's the battery or the two resistors. Now, to find the voltage drop across each resistor, right, with Ohm's law, we know that the voltage is equal to the current flowing through the resistor times the resistance. So if we want to know the voltage drop across R1, we simply multiply the current times R1. So 0.35 amps times 47 ohms gives us 16.4 volts. Let's do the same thing now for R2. It's the same current, notice, right? 0.35 amps flows through all of the circuit elements when they are connected in series, and we get 28.6. Now, these should add up, right, to 45. And if we do the math, right, 16.4 plus 28.6 does indeed get us back to the full electric potential on the battery side. Now, let's do a little thought experiment here. If the 47 ohm resistor is replaced by a 39 ohm resistor, will the current increase, decrease, or remain the same? So how will that 0.35 amps change? Well, if we decrease, right, the resistance from 47 to 39, the total effective resistance will also decrease. So the less resistance we have for the same voltage, the greater the current will be. So we would see an increase in the current. All right, let's look at resistors in parallel. So this is a different way to connect them. They're side by side. That's why we call them parallel. How would we find the total current in this circuit? Now notice the total current is going to split. Some of the current will flow through R1, some of the current will flow through R2. So the total is equal to I1 plus I2. Now I1, we know, is the voltage divided by R1. And I2 is the same voltage divided by R2. Notice both resistors are connected to the same points of the voltage on the battery, right? The top of the resistors are both connected to the plus side of the battery. The bottom of the resistors are both connected to the negative side. So each resistor is going to see the same electric potential or voltage drop across them. So we can write the total current as the sum of this common voltage divided by R1 plus the same voltage divided by R2. So the R equivalent, right, you could rewrite this way, right? Voltage over R1 plus voltage over R2. And this yields a formula that we can use to find the equivalent resistance for resistors that are in parallel. And this one's a little bit more complex, right? In series, we just simply added them. Here we can add the reciprocal values of the resistance to get the reciprocal value of the total equivalent resistance. So 1 over R equivalent equals 1 over R1 plus 1 over R2 plus however many resistors we have in parallel here. Right, so let's calculate the equivalent parallel resistance here, right? And remember the example we had a minute ago had two 20 ohm resistors in series. This problem, we have two 20 ohm resistors in parallel. So we're going to use this formula. So 1 over the equivalent resistance is equal to 1 over 20, R1, plus 1 over 20, which is R2. So we can add them together. They have a common denominator. So 1 over 20 plus 1 over 20 gives us 2 over 20, and that simplifies to 1 over 10. Now, when you solve these types of problems for parallel, make sure you, at the end, right, take the reciprocal to get the equivalent resistance. You don't want to leave your answer as 1 over the equivalent resistance. So 1 over 10, if we take the reciprocal of that, it just simply becomes 10 over 1 or 10 ohms. All right, one more example here. So we have a circuit that has 3 parallel resistors, 60, 30, and 20 ohms. They are all connected across the same voltage source. They're both all 3 of them will have 90 volts across the resistor. In other words, we'll lose 90 volts of potential as we travel across each resistor. So we want to find the current through each branch of the circuit. We want to find the equivalent resistance, which means if we were to take those 3 resistors and replace them with one that would have the same total current, what would that be? And then find the total current that's flowing through the battery, which is the same as the total current flowing through the circuit. All right, so for the first, right, we're just going to use Ohm's law. The current through resistor 1 is equal to the voltage divided by the resistance of resistor 1. So 90 volts divided by 60 gives us 1.5 amps. So we'd have 1.5 amps of current flowing down through that first resistor. Let's do the same thing for the second one. It turns out to be 3 amps. And let's draw it in here, right? We have 3 amps now flowing through the second resistor. And then the third one, we would have even more, right? Because the resistance keeps getting smaller for the same voltage. So 4.5 amps now flowing through. So think of it this way, the total current has to split by these values, 1.5, 3, and 4.5, as it divides itself and flows through the resistors. But the total current, right, is simply going to be the sum of all of those. Now let's find the equivalent resistance here. Here's our formula, right? So this one's a little more complex because we have 3 terms. And you would say, okay, I have to find a common denominator. Don't bother with that, right? Let your calculator do the work. Just take what is 1 divided by 60 plus 1 divided by 30 plus 1 divided by 20, and then take the reciprocal of that, and we find that we get 10 ohms here. So what is our total current, right? It's going to be the voltage of 90 volts divided by the equivalent resistance we just calculated. So 90 divided by 10 gives us 9 amperes. And notice that 9 is the same value that we get if we add up the individual currents, the 3 individual currents that flow through the 3 resistors, right? 1.5 plus 3 plus 4.5 gives us 9 amperes. All right, so let's summarize here the difference between a series and parallel resistor circuits. If they're in series, here's the big idea. They have the same current flowing through the resistors, but they have different voltages. And the equivalent resistance is simply adding R1 plus R2 together. And the total voltage increase across the battery is equal to the voltage drop of V1 plus the voltage drop of V2. For a parallel circuit, we flip it around. They're going to see the same voltage, but different currents flowing through the parallel resistors. And the equivalent resistance is equal to 1 over R1 plus 1 over R2, or I should say 1 over the equivalent resistance. And the total current is equal to the sum of the individual currents as it splits and travels through the 2 resistors in parallel. All right, so that's it. We know how to draw a schematic. We know how to calculate power dissipated in a resistor. We know how to recognize the difference between parallel and series circuits. And we can solve series and parallel circuits for voltage, current, and resistance. All right, that's it. Take a look at the assignment.